Welcome to the AI Research Roundup. I'm Alex, and today we're looking at a paper from the Hugging Face trending list, published on July 28, 2025, just yesterday. This paper introduces a new family of LLMs that can run at over 20 tokens per second on ordinary consumer CPUs, using very little memory. The paper is titled SmallThinker, a family of efficient large language models natively trained for local deployment, and as we'll see, the results are really impressive. It challenges the idea that powerful AI needs the cloud by designing models specifically for local hardware limitations. And right away, the authors show us just how impressive these results are. This first chart plots model accuracy against speed, all tested with an 8 GB memory limit. On the vertical axis is the MMLU score. That's the Massive Multitask Language Understanding Benchmark, which tests general knowledge. Higher is better. Horizontally, we have decoding speed, and you can see SmallThinker 21 BA3B in the top right. It's the fastest and highest scoring model. This performance comes from its clever design, like using a mixture of experts, a technique where only small parts of the model activate at once, saving computation. So how did they achieve these impressive results? Well, the paper's table of contents gives us a clear roadmap. It walks us through the entire process, starting with the model's core architecture, then its pre-training and post-training phases, and finally the evaluation and the special inference framework built for local devices. One really interesting part mentioned in the architecture is the nope-rope hybrid sparse attention. This is a technique for managing how the model understands word order, and by using this hybrid approach, they slash the memory needed, which is key for on-device performance. Okay, so this next diagram gives us a great visual of the SmallThinker architecture. A key innovation is the mixture of experts router, placed before the main attention block. This smart design lets the system predict which experts are needed and pre-fetch them from slow storage, hiding that latency. The attention block itself uses that nope-rope hybrid method, which reduces the size of the KV cache. That's a special memory bank for speeding up calculations. Finally, the selected experts use a ray-glue activation function to create even more sparsity, saving computation. Building on that architecture, this table then details the specific configurations for the two SmallThinker models. We have the 4BA0.6B and the 21BA3B versions. You can see how they scale up. More layers, a larger hidden dimension, which is essentially the model's main working memory size, and more attention heads. Attention heads are like parallel processors that let the model focus on different parts of the text. But the really interesting part is the mixture of experts set up. The larger model has 64 experts, but only activates the top 6, which is how it stays so efficient. And that efficiency really shows when we look at the performance benchmarks. This table compares the SmallThinker 21BA3B model against other strong open-source counterparts across a range of tasks, from general knowledge and math to instruction following with IF eval and coding with human eval. What's remarkable is that SmallThinker achieves performance comparable to QN330B A3B, a much larger model. This result is significant because it's achieved with fewer total and activated parameters, really driving home the point that its efficient architecture delivers top-tier results without the usual computational weight. Alright, moving to the real-world performance, this next table is where SmallThinker's design truly shines, especially under tight memory constraints. We're looking at decoding speeds on different devices, all limited to just 8 GB of memory. All models also use Q40 quantization, which is a technique to shrink the model size for faster performance. On the OnePlus 13 smartphone, SmallThinker is dramatically faster than the QN3 model. This massive speedup comes from that pre-attention router, which cleverly prefetches model parts from storage, completely hiding the usual slowdown. So to wrap things up, SmallThinker really represents a potential paradigm shift. Instead of just shrinking big models, it shows that by designing for local device constraints from the ground up, you can get incredible performance without needing the cloud. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.